next we're going to look at doing some calculus with parametric equations. So the parametric form of the derivative, if x equals f of t and y equals g of t, is dy over dx equals dy over dt divided by dx over dt, where dx over dt is not equal to 0. So basically, if you want to think of it this way, what we're doing on the right-hand side of that is a division here. And if you do keep, change, flip on that division, you'll see what happens is it's kind of like that dt cancels and you're left with dy over dx. Now you can use this repeatedly to find higher order derivatives. So for example, the second derivative would be the derivative with respect to x of the derivative with respect to x. And what you would be doing then is taking the derivative with respect to t of dy over dx and dividing it by dx over dt. So that's what's going on here. That's why we end up with this d squared y over dx squared notation that you've seen in the past. That's actually where it comes from. And then you can do the same thing with the third derivative as well, and so on and so forth. So this example says find dy over dx for the curve given by x equals cosine of t and y equals sine of t. So I know that dy over dx is going to be equal to dy over dt divided by dx over dt. And since since y is equal to sine of t, the derivative with respect to t of that would be cosine of t. And x is equal to cosine of t, so the derivative with respect to t of that would be negative sine of t. So I end up with negative cosine of t over sine of t, which is negative cotangent of t. And of course, we need to ensure that t is not, that the denominator here is not equal to 0. So that means t cannot be equal to k times pi for any integer k. Just a little caveat that makes this thing well defined. Now, of course, you can always find the rectangular equations for this by eliminating the parameter and then finding the derivative there also. That would work as well. This one wants us to find the first and second derivative and find the slope and concavity if possible for this particular parametric equation at t equals 1. So I'm going to find, because this one's a little more complicated, let's go ahead and find dy over dt, which is 3, and dx over dt, which would be the derivative with respect to t of t to the 1/2 power. So that's 1/2 t to the negative 1/2, or 1 over 2 square root of t. So dy over dx then is going to be 3 over 1 over 2 square root of t. And when you multiply that out, you get 3 times 2, which is 6 square root of t. The second derivative is going to be the derivative with respect to t of dy over dx, 6 square root of t, divided by the derivative with respect to x, the derivative of x with respect to t. So this will be 6 times 1/2 times t to the negative 1/2 divided by 1 over 2 square root of t. So that's 3 over, because the 6 and the 2 cancel and give it 3, over the square root of t. Keep, change, flip gives me 2 square root of t over 1, which gives me 6. So when t equals 1, the slope is dy over dx at t, which is 6 square root of 1, or 6, and the concavity, because the second derivative equals 6, which is greater than 0, we can say that for the entire, or at this point, it is concave upward. So slope and concavity. This one says find all points, if any, of horizontal and vertical tangency to the curve. So I'm going to start by finding my slope, and I'm going to find my I'm sorry, I'm going to start by finding my derivative. So I'm going to find dx over dt, which is 1, dy over dt, which is 3t squared minus 3. And I know that m would be dy over dx, which would be 3t squared minus 3 over 1, or just 3t squared minus 3. Now, we know that this thing is undefined when dx over dt equals 0. And in this case, it's basically, this thing is dy over dt divided by dx over dt. So the slope is equal to 0 when dy over dt equals 0. And the slope is undefined when dx over dt equals 0. So a horizontal tangency, horizontal lines have a slope of 0. So we're talking about horizontal tangency being when dy over dt equals 0. So for this particular example, that would be 3t squared minus 3 equals 0. Or if you factor out the 3 and divide, you get t squared minus 1 equals 0. T squared equals 1, so t is equal to plus or minus 1. So that's going to happen there. And x at that point is, if t equals 1, x equals 5, and y equals 1 cubed minus 3, which is negative 2. And at t equals negative 1, x equals 3, and y equals 2. So you've got 2 points of horizontal tangency. Vertical tangency, remember, a vertical line happens when the slope is undefined. So that's when dx over dt equals 0. But our dx over dt is 1. So there are no points of vertical tangency for this particular curve. Let's do another one. We want to find horizontal tangency. Remember, that happens when dy over dt equals 0 and dy over dt equals 36. So if you set that equal to 0, it doesn't. So there's no points of horizontal tangency. Vertical occurs when dx over dt equals 0. So that would be 6t plus 6 equals 0. 6t is equal to negative 6, and if I divide by 6, I get t equals negative 1. X would be 3 times negative 1 squared plus 6 times negative 1 plus 7, which is 4. And y would be 36 times negative 1, which is negative 36. So the only point of vertical tangency is 4, negative 36. There are no horizontal tangencies here. This one says, find the equation of the tangent lines at the point where the curve crosses itself for x equals 2 sine of 2t and y equals 3 sine of t. So what I'm going to do for this one is I'm going to attempt to graph this in the rectangular coordinate system. So I'm going to make the plane curve here. And it doesn't give us any parameters for t. So we're just going to go like maybe from negative pi to pi so we can get at least one full period of these things. So I'll graph negative pi, negative 3 pi over 4, let's see, negative pi over 2, and we'll do negative pi over 4. I'll go 0 and then kind of copy that in the positive direction. Intervals of pi over 4. Okay, so I'm going to plug that in for x and y. And if I plug in x equals 2 sine of negative 2t, I'm going to get 0. If I plug in the negative 3 pi over 4, I'm going to get 2. If I plug in the negative pi over 2, I'm going to get 0. If I plug in the negative pi over 4, I'm going to get negative 2. The 0 will give me 0. Pi over 4 will give me 2. And if I plug in pi over 2, I'm going to get 0 because it's going to be 2 times pi over 2. 3 pi over 4 will give me negative 2, and pi will give me 0. So this has that bouncing back and forth oscillating behavior that you expect. 3 sine of t, if I plug in the negative pi, I get 0. If I plug in the negative 3 pi over 4, I get negative 3 root 2 over 2, which is about negative 2.12. If I plug in 0, I get negative 3. If I plug in negative pi over 4, I get that again, that negative 3 root 2 over 2. The 0 gives me 0. The pi over 4 gives me 3 root 2 over 2, which is about 2.12. And then I get 3 root 2 over 2, and 0. Now when I go to graph this, I'm going to plot 0, 0. I'll have 2, negative 2.112, so we're kind of moving in this direction. And that orientation is important. Then we're going to go down to 0, negative 3. Then we'll have negative 2, negative 2.14 roughly. We'll go back to 0, 0. Now you can see this is the point at which the graph crosses itself. Then we'll have 2, positive 2.12, so we're going kind of in this direction. And then we'll go to 0, 3. And we'll do negative 2, positive 2.14 here. And then back down to 0, 0. So you can see that this pattern is going to repeat itself if you keep going around the unit circle. So the graph will cross itself whenever x equals 0 and y equals 0. So that's going to be our point. But we're looking for the equation of the line, the tangent line at that point. So I'm going to find the slope. I'm going to find the derivative, which is dy over dx. And that's going to be dy over dt divided by dx over dt. And of course, dy over dt in this case is going to be 2 times the derivative of the inside times the derivative of the outside. And then dx over dt is just going to be 3 cosine of t. So I get, and I think I did those backwards. I did. See, I make mistakes sometimes too. dy over dt is 3 cosine of t. dx over dt is the 4 cosine of 2t. It happens to all of us. Okay, so the two places that we know for sure that, that this is going to happen are at t equals 0 and t equals pi. So at t equals 0, m would be 3 cosine of 0 divided by 4 cosine of 2 times 0, which is actually 3 times 1 over 4 times 1, or 3/4. So the equation would be y minus 0 equals 3/4 times x minus 0. That's my x1 and my y1. Or y equals 3/4 x. And at t equals pi, m is going to be 3 cosine of pi divided by 4 cosine of 2 pi. So this will be 3 times negative 1 over 4 times 1, or negative 3/4. So we would have y minus 0 equals negative 3/4 times x minus 0, or y equals negative 3/4 x. So those are my two tangent lines. And if you were to try to graph them, they would look basically like this. That would be one, and that would be the other.